Today, we're diving into a concept that's so fundamental, it's basically the language of modern mathematics, logic, and even computer science. Yep, we're talking about sets. So, let's kick things off with a little story. Way back in the 19th century, there was this mathematician, George Cantor, and he'd look at the world around him. His wife's makeup collection, the clothes in a closet, books on a shelf, and he saw this kind of beautiful, organized chaos. He started to wonder, hey, is there a way to apply some real mathematical structure to the simple act of just grouping stuff together? And that curiosity led him to ask a really, really important question. What's the actual difference between just some random collection of things and a mathematical set that we can actually work with? Well, the answer, the secret sauce, if you will, is this idea of being well-defined. What that means is the rule for whether something belongs in the group has to be completely 100% unambiguous. There can't be any room for opinion or debate. So there it is, our official definition. A set is a well-defined collection of distinct objects. For any object in the entire universe, you have to be able to say with absolute certainty, yep, that's in the set, or nope, it's out. And everyone, no matter where they are in the world, would come to the exact same conclusion. And this slide just shows that difference so clearly. On the left, a collection of vowels. That's a set. We all agree they are A, E, I, O, U. Easy. But on the right, a collection of interesting books. That's not a set. Why? Because what's interesting to me might be totally boring to you. It's completely subjective. Okay, so let's put this idea to the test. What do you think about a collection of good hockey players? Does that count as a mathematical set? Just think about that for a second. And the answer is a definite no. That word good is just too vague. A player who seems good today after winning a big game might not look so good next season. The criteria changes from person to person and over time, so it's not well defined. It's a collection for sure, but not a set. So we get what a set is, but how do we actually, write one down using math language? Let's get into the specifics of how you actually build these things. We're going to start with the most direct method out there, roster form. Some people call it tabular form. It's basically where you just list out every single member or element of the set. And this lays out the 4 simple rules perfectly. First, you always use curly braces. Second, you separate each item with a comma. Now, numbers 3 and 4 are the really big ones. You never repeat an element, and the order you list them in makes absolutely no difference at all. Right, so that no repetition rule is crucial. If we're building a set from the letters in the word school, even though there are 2 O's, we only list O one time in our set. Each element has to be unique. And this isn't just some random math rule. This idea is foundational in computer science for stuff like making sure every entry in a database is unique. Okay, this brings us to a key idea called cardinality, which is really just a fancy word for the size of a set. Now, if you look at set A here, your first gut reaction might be to say, hey, it has 6 elements. But remember rule number 3, no repetition. When we actually count the elements, we're only counting the distinct ones. So the set A is really just 1, 2, 3, and that means its cardinality is 3. Roster form is awesome for small, simple sets. But what if your set has thousands of elements? Or what if it has an infinite number? You can't possibly list them all out. We need a smarter way, a more elegant solution. And that solution is called set builder form. Instead of listing the elements one by one, you just describe them. You state the rule or the property that an object has to meet to get into the set. This slide shows it perfectly, side by side. Both of these represent the exact same set, the set of vowels. The one on the right in set builder form reads like this. V is the set of all elements X, such that X is a vowel in the English alphabet. It's just the proper mathematical way of stating the rule. All right, so now we've got the language down for how to define sets and how to write them. Now we can start sorting them into different categories based on their properties, like how big they are and what's inside. Let's explore some of the most common types of sets you're going to run into. As you can see, there are a bunch of ways to classify them, and each of these names has a very specific, very precise meaning. First up, we have the empty set, which is also called the null set, and it's exactly what it sounds like, a set with absolutely nothing in it. For example, think about the set of natural numbers that are less than 1. There aren't any, right? So its cardinality is 0. Next up is the big difference between finite and infinite sets. A finite set is one where you could, at least in theory, count all the elements and actually get to an end, like the set of months in a year. An infinite set, well, that's one where the counting would just go on forever and ever, like the set of all natural numbers. Now, this slide points out a really subtle but super important distinction. Take a look at that first example. Set A and set B both have 3 elements. They have the same size, the same cardinality. That makes them equivalent. Okay, now look at the second example. They don't just have the same number of elements, they have the exact same elements. They're just in a different order. That makes them equal. So here's the big takeaway. All equal sets are also equivalent, but as you can see in that first example, not all equivalent sets are equal. And just like that, we've come full circle. We started with George Cantor just looking at everyday stuff. And from that really simple observation, we've built up this powerful and precise system for creating mathematical order out of the world. And look, this isn't just some abstract math exercise. The ideas behind sets are what power the databases that run pretty much everything. They form the basis of logical reasoning, and they're the absolute foundation for higher level math like calculus. So now that you have this incredible tool for organization, the real question is, what are you going to build with it?